fellow South African learners. My name is Mtutuzi Dlamini. I am a lecturer at Ehlanzeni TVET College under the engineering department, where we offer electrical infrastructure and construction. The subject that we'll be looking at today is electronic control and digital electronics, NQF level 4. And the topic is still fundamentals of electronics. So now we shall look at what we call bipolar junction transistor amplifiers. That's our topic. Bipolar junction transistor amplifiers. Well, by now I know that from your past experience in level 2, level 3, you can now explain what an amplifier is. So we won't dwell much on explaining what an amplifier is, but in a nutshell, we know that an amplifier will have an input signal and then will tend to make it gain or more and have an output signal which has gained from the input signal. So that being said, almost all electronic systems, I can even safely say every electronic system has some kind of an amplifier. Okay, e.g. your public addressing systems, your radios, your TVs that you are looking at now, your CD players, your cell phones, you can name them. Those are all electronic systems, and they will always have some kind of an amplifier. Anyways, let's start with what we call a bipolar junction transistor. I will not go deep on it, as it was discussed earlier in your level 3 and your level 2 syllabus. So a BJT, it's simply BJT for bipolar junction transistor. So each time you hear me say BJT, by now you know that it's a bipolar junction transistor. So in its circuit symbol, this is a circuit symbol of a bipolar junction transistor. I will use one kind of transistor. We've got two types. We've got what we call an NPN and a PNP configurations. So now I'll only use an NPN for explanation, where we know that in this transistor I've got three terminals, one named the collector, the other one named the base, and the other one named the emitter. We always know them by the arrow here. Once your terminal has an arrow here, it simply tells us it's the emitter, and the other one could be the base, and the other one could be your collector. So we can simply say it's a three-terminal device which is capable of switching and amplification. Those are the two main purposes of a transistor: switching and amplification. So if you see a transistor in a circuit, you should know that it is there for either as a switch or as an amplifier. So we shall look into a transistor as an amplifier, as we have looked as a transistor as a switch in our past levels, which is former levels, which is level 3 and level 2. So we shall now look into a bipolar junction transistor as an amplifier. So naturally, a BJT or a bipolar junction transistor is a current amplifier. But some transistor circuits are designed for voltage and power amplification. So how does an amplifier look? How does an amplifier look like? An amplifier, let me just draw an amplifier circuit. An amplifier, it's a circuit which loosely we can simply say looks like that. Once you have all these components surrounding this transistor, we can now say we have an amplifier. We normally name the components according to the terminal they are connected to. Remember, we said it's a collector, so we shall name it an RC. It's a base, we shall name it an RB. We can also have other components here, which we'll call RE resistance in the emitter, capacitor in the emitter. We shall call this a CC, which is a capacitor on the collector. So now, we can also have CP, capacitor on the base. There is where we have our output. There is where we have our Vin, our input. So basically this is what we call a amplifier circuit. So how does a transistor become an amplifier? It leads us to what we call the operating regions of a transistor. You do remember we've got 3 of them. Operating regions of a transistor. If you were to name them, I know you would say one is what we call the cut-off region. Okay, that's one of the regions we have. What happens in the cut-off region is that if you look into our transistor, we have the base and the collector. So we have a junction here and we have a junction there. We've got 2 junctions. And this junction, it's called the base collector, and this junction is called the base emitter. So in a cut-off region, it simply tells us that this transistor will have both the base emitter, if you see me writing BE, base emitter, and base collector junctions, all reversed biased. So it simply means that both these junctions are in reverse bias mode. That is to say, we can have IB, our base current, which controls this transistor. Our base current can be even less than 0 microamps. That is to say, we actually have no current in the base. And we now know that if we don't have current in the base, there will be no current flowing in the collector and no current flowing in the emitter. So what do we mean? We say the base is what we call the control electrode of transistors. So if you increase IB, the collector current will also increase with respect to the increase in IB. So if we say we can keep IB at below 0 microamps, that is to say the transistor in that region, the region 1, which is the cutoff, the transistor is said to be off. So it's in an off state. So the second region is known as the linear. The linear, or some textbook will call it an active region. In this region, we have our initially we say the base emitter is forward biased. Base emitter is forward biased. Forward biased, while the base collector is reversed biased. So you can see that in this region we have one of the junctions being forward biased, which is the base emitter during this region, but the base collector will be in a reverse bias mode. So it simply means that we can now increase a level of IB so that we can start forward biasing the base collector region. Anyways, we shall talk about this. This is the region we are mostly concerned about. But let me talk about the last one, which is called the saturation. The saturation. In the saturation, we now have both base emitter and base collector regions. Base collector junctions forward biased. So if they are forward biased, it simply means that we can have IB maximized. Okay, once we maximize IB, it simply means that There is a time when we increase the value of the base current in such a way that IC can no longer increase. Remember, we say the increase in IB is proportional to the increase in IC. So now, there is a point where we will increase IB such that IC can no longer increase. We normally say in that we have saturated the transistor. It can no longer do any increase. So we normally say the transistor is saturated. It makes the transistor to look like a wire, like less resistance. So we normally say it is fully on. So if I were to ask you, since we say a transistor is used for switching and amplification, you will see that in these two regions, it has got off and on, isn't it? Which electrical device does an on and off, or switches on and off? Okay, I've already said it's a switch. So in these two regions, that's where the transistor is being used as a switch. Well, our topic today is no longer on switching. It's not on switching, it is on this region. You will see that IB will be minimum, IB will be maximum. So you can now see that in this linear active region, you can start increasing your IB just above cutoff, but you cannot reach your maximum. So it simply means that you can increase your IB from just above cutoff, but you cannot reach saturation. So that region which is between cutoff and saturation is known as your active or your linear region. That can be characterized by some graphics, if I may. So, what do we mean? For us to dissect these three regions, we can have this as a characteristic curve of a transistor. 1, 2, 3, 4. Doesn't matter, 1, 2, 3, 4. So, somehow, we can now say, if we increase IB, IC might also increase. So we shall call this a characteristic curve of what we call a transistor amplifier. So, from there, we have our output current IC, we have our output voltage VCE. So, it simply says that if I were to raise IB to be minimum, IB at its minimum, and if I continue somewhere here, I will have IB to be maximum. Okay, that being said, we said if IB is minimum, it will be off. So anything below IB minimum, will be what we call the cut-off region. So this is our cut-off region. So anything that will appear across IB maximum, this is where we call the saturation region. Saturation region. So you can say that now you have only this part, just above IB minimum, but before IB maximum. This is the region where we say it's linear or active. This is the linear or what we call active region. This is where the transistor is being used as an amplifier. So this is the region where we say the transistor is being used as an amplifier. So that will lead us to what we call biasing the transistor now. What do we mean by biasing the transistor? It simply is a method of establishing predetermined values of voltages and current at various points of a circuit so that we can be able to set an appropriate operating point for the transistors. Transistors need to operate at a certain point. They have what we call specifications. They are when you buy a transistor, there is a specification that is written on the transistor, which tells you how should the transistor be operated, its maximum and its minimum values. So what do we do by then? It simply means that for us to bias the transistor, we need to know a lot of information about the transistor. So, first of all, how do we bias the transistor? Let us look at how we bias the transistor. Biasing of a transistor. And mind you, in this case, biasing is not what you are used to. Biasing is not what you are used to. In electronic, when we talk of biasing, we are talking of this method of identifying voltages and currents. So, now, let's say we take our transistor, we forward bias the base emitter. Okay, we forward bias the base emitter by 0.6 volts. Let me draw the circuit. Biasing a transistor. Biasing a transistor. RC. If we bias the transistor, we need what to call a base emitter voltage. We need a base emitter voltage, which we shall call VBE. Okay. So we need a forward voltage, which means it forward biases this junction, and this forward voltage is around 0.6 volts. Some textbooks will say 0.7 volts. You will not be punished for any of those. Okay. So with that transistor, with that being our first way of first step in passing the transistor, it simply says that our base collector now, remember we've got a source here, we've got a source which looks like this. So our base collector now, our base collector will be in a reverse bias mode. So base collector in a reversed bias mode. So it simply says the reverse voltage being a value between, we call this source VCC, and we call this source with this part VCE. So it simply means that if we were to do that, VCE can be a value within any of the value from 0 to the value of VCC. So for you to bias a transistor, you need, as an amplifier, this is the condition, or these are the conditions that must be met. So now, you must also take into consideration the maximum values across the transistor, Q, and you should also take the maximum values of IC that will be allowed into the circuit, and you can also see that the maximum power that can be dissipated by the transistor. So those are the points that you should consider when you are designing an amplifier using a bipolar junction transistor. So now, there is what we call gain. Remember, we say an amplifier has some kind of gain. You put an input signal and you receive a bigger signal. So it simply says you have a signal there and you have a bigger signal there. So that's gain. How much of this signal have I gained from this signal? It is called gain. It is denoted by the letter B. It is now beta, so it was called static gain. That is the gain you can find or you can determine of the transistor without any input or external signal. So, how do we calculate gain here? This part of the gain, as you've seen the transistor, this part of gain comes with the specifications on the transistor. So it could be given, this transistor has got a beta of, or a gain of, blah, blah, blah. So now, we call this the DC or static gain because nothing has been introduced as an external signal from the amplifier. There is no external voltage or input signal. So we can call it a static gain. We want to look into the values of this without any external signal. So gain can also be determined by values called a transistor, which we can say gain is some kind of output current over input current. Now, input current is the current that will be in the base. Output current is the current that will be taken from the collector. That's our output. You see we have written out here, there's in there. So, it can simply be denoted like IC over IB. So you can now find the gain of this transistor by knowing the values of your collector current and your base current. So that way, they will give you the output of, or what we call the gain. So it means you can also find your output current if you know your gain and your input current. You can now determine your output current by saying, since we are making this the subject of the formula, it should be BIB. That is to say, your output current will be multiplied by the gain of the transistor plus multiplied by the gain of the transistor and the input current of that transistor. So, learners, questions that may come out of this, because this was just an introduction of an amplifier, is for you to understand what a bipolar junction transistor is. What are the operation regions of it for a BJT? Why? How can it be used as a switch, and when can it be used as an amplifier? You should also know the input and output characteristics, where we say these are output characteristics of a bipolar junction transistor. You should also understand the methods of biasing a transistor. So in electronics, we know that biasing doesn't mean that what you know, it's just determining certain values of the transistor at given points. You also know now how to bias a transistor to operate as an amplifier. So, now, all those kind of questions, since we've got this understanding of the transistor, it will be now easy for you to answer all those questions and examination, and for you to understand the amplifier in its own, because just for preparing for the exam alone is not enough for electronics. You need also to understand, to go deep and understand how you will be tackling amplifier circuits. So, for further explanation, there is our page, which is Ehlanzeni college.co.za. We can also find it, or we can also be found in Guma media, or what you call social media platforms, where we have our Facebook page and our Twitter handle, #Ehlanzeni College. For now, I thank you. Till we meet again next time.